All right, hello. This is the solutions for assignment 12. So below in this graph, I have two waves. Draw the resultant wave using your knowledge of superposition. So we have the large red wave that reaches a peak of 3 at pi over 2 and a lowest point, a minimum of -3 at 3 pi over 2. Then the blue wave, it has a lowest point at pi over 2, so -1, and a maximum at 3 pi over 2, +1. So the amplitudes, we're simply just going to add them at each point. At 0, at the origin, they are both at 0. So we know it's going to go through that point. At pi, they both go through that point at 0, and at 2 pi. They're both 0 at all of these points, so we know that our resultant wave is going to go through each of these 3 points. Now, the amplitude at pi over 2 of the red wave is 3, of the blue wave it's -1. So together, that is a +2 amplitude. Very, very similarly, just with opposite signs. For the 3 pi over 2, the red wave is at -3, the blue wave is at +1, so that leaves us at -2. So, tracing through our graph here, we know it's going to look something like this. Sorry for that noise, it's my hand scraping or sliding across the iPad, getting stuck. Okay, so that was our answer there. 2. Polynesian navigators could reliably find islands that were far beyond the visible horizon. Without modern technology, they often detected islands by observing subtle patterns in ocean waves. What are these patterns, and how are they created? These are interference and or, depending on the type of island or how many islands and how they're placed, interference and or diffraction patterns. So that was for one of the points. The other one was for saying that they are created by waves passing between and around distant islands. So as a wave passes an island or passes between two islands, it will, or if it passes by multiple islands, it will interfere and diffract with itself, creating a pattern of waves on the surface that the Polynesian navigators learned to use to identify the location of islands that they couldn't see. Number 3 here. So a mass on a spring oscillates 45 times in 18 seconds. Find the frequency of oscillation. So from the formula sheet, we see that frequency is equal to the number of cycles divided by delta t. And plugging in our numbers here, we have 45 cycles over 18. That gives us a frequency of 2.5 hertz. For the period, a couple of ways you can find this. You could have used the similarly looking period equals delta t over number of cycles formula. Instead, I felt like using the formula where period is equal to 1 over the frequency. So that is 1 over 2.5, which makes the period equal to 0.4 seconds. C. If the spring is replaced with a different spring that increases the frequency by 20%, how many oscillations would occur in 18 seconds? So, how many oscillations is also known as the number of cycles. And rearranging the equation I used above with frequency, number of cycles, and delta t, for number of cycles, I get this is equal to frequency times delta t. And I want to increase the frequency by 20%. So when I sub in, I'm going to have a multiplier of 1.2 in front of my frequency of 2.5 here. This is going to be what increases my frequency by 20. And we still have 18 seconds. My final answer ends up being 54 cycles. Once you plug that all in. So that was questions 2 and 3. Question 4. A spring and mass oscillate with a period of 0.8 seconds. Find the value of square root of k over m. So from the formula sheet, we see that frequency equals 1 over 2 pi times the square root of k over m. So I'm using this formula just because I see that the square root of k over m is already in it. So that's why I'm choosing to use this one. Rearranging, I got the square root of k over m is equal to 2 pi times the frequency, which is also equal to 2 pi over the period. So plugging in, I get 2 pi over a period of 0.8 gives me an answer for what my square root of k over m is equal to as being, now you could say that this is 5 pi over 2 as an exact answer, or 2.5 pi, but most of us used a decimal answer, so I will provide a decimal answer here. So it's equal to approximately 7.854. For B, find the angular velocity. So here I'm going to be using the formula frequency equals omega over 2 pi. And then to find angular velocity, that's going to be omega equals 2 pi times the frequency, which is also 2 pi over the period, which gives us 2 pi over 0.8. And plugging that in, we get 7.854 again. Comparing the two values, they are identical. So you can conclude that, therefore, omega, the angular velocity, is equal to the square root of k over m for the mass on a spring. 5. A pendulum on Earth has a frequency of 0.6 hertz. Determine the length of the pendulum. 2 points. So I'm going to go ahead and use my frequency formula, because this time I'm given frequency. So that's equal to 1 over 2 pi times the square root of g over L. Awesome. So we want to find the length of the pendulum. So rearranging to get L on its own, I'm going to have the square root of g over L is equal to 2 pi f. I'm going to square everything. So I get g over L is equal to 4 pi squared f squared. Multiplying everything by L and dividing everything by 4 pi squared f squared, I get L equals G over 4 pi squared F squared. Plugging in some values here. L equals 9.8 because gravity on Earth is 9.8 on average. On the bottom I have 4 pi squared, and my frequency is 0.6 squared. Plugging all of that in, I get a length of 0.6895 meters. B, if the same pendulum is taken to a planet where the period is now 2.6 seconds, what is the acceleration due to gravity on this new planet? So, I'm going to go ahead and use a very similar equation here. I'm going to say that 1 over t, the period, is equal to 1 over 2 pi times the square root of g over L. Now this is the exact same formula as above. What I have done is I've replaced the frequency with 1 over the period. So I took two formulas from the formula sheet to create this one here. And now I'm going to essentially do the same thing where I solve for g, skipping a couple of steps. G is equal to 4 pi squared L over t squared. Plugging in some values, G is equal to 4 pi squared times the L that we just calculated, so 0.6895, all over the period squared. And this gives us a G of 4.03 meters per second squared. So that is our answer for 5 and number 4 as well. 6. A wave generator creates a wave that completes 75 cycles in 30 seconds. The wavelength of the wave is 0.42 meters. Find the period of the wave. So I'm going to use the formula that says the period is equal to the change in time over the number of cycles. This is 30 over 75, which gives me a period of 0.4 seconds. Find the frequency of the wave. I'm going to use the frequency is equal to 1 over the period, which is 1 over 0.4, which gives me a frequency of 2.5 hertz. C, find the wave speed. So here we have V equals F times lambda. This frequency here is given by 2.5, and lambda is 0.42. I got that from the beginning in the question here. It tells us that the wavelength of the wave is 0.42 meters. So that is where that 0.42 came from. And this gives me a wave speed of 1.05 meters per second. D, find the new wavelength if frequency is kept constant and the wave speed is increased by 15%. So rearranging my previous wave equation, I have wavelength equals velocity over frequency. This is a factor of 15% larger than our original wave speed, so we multiply by 1.15 to get 15% larger, and we divide by the frequency, And that gives us a wavelength of 0.483 meters. Perfect. Number 7. Find the wavelengths of a 1200 kilohertz AM radio station and a 102.1 megahertz FM radio station. 2 points, 1 point each. So I will do AM over here, FM over there, AM first, using the wave equation slightly rearranged for light. For the wave equation for light is just going to be that the speed of light is equal to the wavelength times the frequency. Rearranging that for wavelengths, just like how we did in the previous question, is C over F, which is 3 times 10 to the 8 over the frequency, which here for the AM we have 1200 times 10 to the power 3, which gives us a wavelength of 250 meters. For FM, it's the same formula with the same speed of light in the numerator, this time divided by the 102, put the decimal in the wrong spot, divided by the 102.1 times 10 to the 6 megahertz. So this time we have an exponent of 6. And plugging that in, we get 2.94 meters. So that was for questions 6 and 7. Question 8. This was the larger of the questions. A wave is described by the following function. Y of x and t is equal to 0.05 sine of 2 pi times the x divided by 0.4 minus t divided by 0.02. I ask you to state the amplitude, wavelength, period, frequency, and wave speed for 1 point each. The amplitude was just that first variable, or that first number out front, 0.05. The wavelength given to us was 0.4, what is underneath the x. And we're not given units here. We can assume they are standard base units, but we're not given units, so I can just leave them as they are. The units aren't what's important in this question. I didn't take off any marks for units in this question, but if you did add units, good for you, I guess. Maybe they were right. I don't know. I wasn't looking to mark the units for this question. So from here, we know that, well, looking at the formulas, let's go here for now. What I'm looking at is this formula right here. This one. So this is 2 pi over the wavelength in the brackets times x minus vt. So if I were to multiply that 1 over lambda through, I'd be left with 2 pi x over lambda minus vt over lambda. This is what I would be left with the amplitude times sine in the beginning here. So what I'm seeing is that, yes, x is over lambda, so we have the right wavelength of 0.4, and t, v over lambda, is being multiplied by t there. So we know that 1 over 0.02 is equal to v over lambda from our formula. rearranging, we can say that V equals lambda over 0.02. So I just multiplied everything by lambda here. That's all I did. And we know what our lambda is. That's 0.4 over 0.02. Gives me a wave speed of 20. We also know from our wave equation that velocity, the wave speed, is equal to frequency times the wavelength. So rearranging for frequency, that is V over lambda, which is, well, we could plug in our numbers, 20 and all of that, but we also know that these are the same. I'll erase that. These are the same. These are both equal to V over lambda. So the frequency is then also equal to 1 over 0.02. So the frequency is 50. Rewrite that so it's a little better. Is 50. Lastly, the frequency is also equal to 1 over the period. So therefore the period has to be 0.02. So this is what I was looking for right here. B, rewrite this function, this wave function using cosine. Write it in the following form. I give you a formula there to follow. And phi is the phase shift specifically in radians. So, writing this out, I get y xt equals a, so that's my amplitude of 0.05 times the cosine Now, following this, I have x over my wavelength, which is 0.4, minus my frequency, which was 50, multiplied by t. Now, my phase shift here, I know that sine theta equals cosine theta minus pi over 2. So I will add minus pi over 2 as my phase shift here. You're more than welcome to graph that in Desmos to prove it to yourself that this phase shift does work. And this was the correct answer here. There we go. That was the correct answer there for part B. C, verify your cosine function by substituting in your values from part A. Then, so that's what we just did. Then, by substituting in x equals 100 and t equals 30 to your cosine equation and the given sine equation. So basically we're verifying that the original equation given to us in the very beginning, is equal to the equation that we just built in part B. We're just verifying that this is true. So plugging in for the sine equation here, we get, and I'm going to call this green. This is going to be a green function. So y of 130, y at both of these values, plugging in, you should get exactly 0. But, so writing this out in full, 0.05 sine times 2 pi times x over 0.4 minus t over 0.02. Close off all the brackets there. Oh, I have x and t. I was supposed to have 130. This equals exactly 0, not 0 point something, exactly 0. This is because if you go through and do the math, you end up getting an integer multiple of pi inside of sine. And as we saw earlier on, a sine wave at any integer multiple of pi, so here it's 0 pi, 1 pi, 2 pi, it is 0 at all of those points. So for that reason, it is equal to 0 here as well. If you punch this in your calculator, you must use radians, not degrees. Radians will give you an exact answer of 0. So for the other one, it's going to look very similar. And again, if you plug that into your calculator using radians specifically, you will get an exact answer of 0. Therefore, verified they are, in fact, the same. So the green y is equal to the red y. Done. So if you plugged it in for degrees, I think you got something like 0.004, a couple of other numbers after that, something in that range. What I was looking for is specifically radians. You should have used specifically radians because your phase shift is in radians. And I almost tell you to use radians here. I do highlight in bold that the phase shift is in radians. So hopefully that is what triggered that part of your brain to remind yourself, hey, I should probably put my calculator in radians for this. 9. A string of length 1.5 meters is fixed at both ends. Waves on the string travel with a speed of 120 meters per second. Part A, write the first 3 wavelengths that allow for resonance. So I'm going to do lambda 1, lambda 2, and lambda 3, like this. From our resonance formula of L equals n lambda n over 2, I can rewrite that as lambda 1 equals 2L over 1, where L is equal to 1.5 meters. So this is equal to 2 times 1.5. So lambda 1 is equal to 3 meters. Lambda 2. This is equal to 2L over 2, which is just equal to 1.5 because the 2's cancel. So lambda 2 equals 1.5 meters. Lambda 3. This is equal to 2L over 3, which is equal to 2 over 3 times 1.5. So lambda 3 is equal to just 1 meter. And that was for part A. For part B, find the corresponding frequencies for each of the 3 wavelengths in part A. So I'm going to set this up the same way. For frequencies 1, 2, and 3. And I'm going to use the wave speed, or the wave equation here, rearranged for frequency. So frequency equals velocity over lambda. That is the equation I'm using here. Remember again, in the very beginning of the question, velocity equals 120 meters per second for the wave speed. So plugging in these values, I get to F1 equals 120 over 3. And this is equal to 40 hertz. And that is the answer for that part. Setting up for F2, this is 120 over 1.5. So F2 is equal to 80 hertz. And F3 is equal to 120 over 1, which gives us 120 hertz. And that was the full assignment 12. Again, if you have questions, please just email me or ask me in class.